Here's a polarity quiz tutorial. This does involve a lot of steps. You need to probably go back and review a few things. This kind of thing is also tutored all over YouTube. Also, you can contact me for more specific questions. So you're going to want to write this down, that a bond is polar if the electronegativity difference is 0.5 to 1.9. The difference between them. It's nonpolar if the difference is 0 to 0.4. Now when I say difference, I mean using the electronegativity chart. So if you had an N and O bond, that would be a polar bond because the difference between them is 0.5. If you had a bond between P and S, you would have a nonpolar bond because the difference between them is 0.4. So the basics of this are you're going to need to know how to do a Lewis dot structure. I can demonstrate on number 1 again. Number 1 would be P, F, 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 F. Now, according to your periodic table, fluorine has 7 valence electrons. Phosphorus has 5 valence electrons. So we're going to use those odd ones, the 7th one and the 5th one, and we're going to use them for shared pairs. So fluorine has 2, 4, 6 outer valence electrons, and the 7th one, 2, 4, 6, and the 7th outer one, 2, 4, 6, and 7, 2, 4, 6, and 7, 2, 4, 6, and 7. Well, look how many bonds we need to make. 5, right? And how many valence electrons does phosphorus have? 5. So there's one of them, and I'll share a pair. 2, and I'll share a pair. 3, 4, and 5. The thing to consider is, do we need a resonance structure because we need to make a double bond or anything? Resonance structures are shared double bonds? Nope. Is it positive or negative overall? Nope. It is an octet violation because the phosphorus Venn diagrams, if you do this, as having 2, 4, 6, 8, 10 valence electrons, so that's an octet violation. And you have to do all this just to get within striking distance of the polarity. So, could it be polar? Well, there are 2 ways to look at it. Are the bonds polar between P and F? The bonds definitely are polar because the difference is 1.9. In fact, they're very, very polar. However, you're going to also need to visualize this using your molecular geometry chart. So I have a central atom surrounded by 5 bonded atoms and no extra cloud, no extra unbonded pairs on the central atom. So I'm going to look at this. Central atom with 5 bonded atoms and no extra clouds on the middle is this. So my answer is also trigonal, bipyramidal, bipyramidal I'm told it is. Okay. And is it polar? Well, these bonds are all polar going, we said, outward to the fluorine because 4 is a lot bigger than 2.1. So yes, these are polar bonds going outward toward the fluorine. However, if you check your molecular geometry chart, you will see that this is symmetrical. It's fluorine, 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 fluorine. And yes, in this case, all the fluorines would be pretty negative because they're pulling those electron pairs to themselves. But you can't mentally draw a line through the middle anyway, any direction, and find the positive side because you find negative, 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 and there's no positive side to this. And there must be a dipole moment. You don't have to write this, but I'm going to do it this time. There's no dipole moment. And di means 2. You don't have 2 poles like north-south on a magnet. There's only one situation here where on the outside they're all negative. So this is non-polar. let's try 3 because it makes a real good point. So 3. I have P and F, F, F. Fluorine has 2, 4, 6 and the 7th one, 2, 4, 6 and the 7th one, 2, 4, 6 and the 7th one. Phosphorus, remember, has 5 valence electrons. So when you use 5, that's use 1 of them, make a bond, 2 of them, make a bond, 3 of them, make a bond, and that leaves me 2 extra, so there's an unshared pair on phosphorus. So now I have 3 bonded atoms and a cloud. That would be trigonal pyramidal. Are the bonds polar? Well, we just said before that this is 2.1 and this is 4.0, right? So yes, they very much are polar. Is this molecule symmetrical, though? No. I can draw a line through the middle, like there, that makes the sides very much not the same thing. This bond is being drawn this down, 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 and so in general, the shared pairs are being drawn down. And that even makes the phosphorus be a little bit plus, because it lost some of its negative electrons. The phosphorus is a little bit plus, which means that this cloud here, made up of negative electrons, gets pulled downward. So even the cloud sort of shrinks downward. And so overall, there has very definitely been a travel of the negative electrons a bit to the bottom and away from the top, very definitely in one direction. And our polarity will be downward, or at least toward the fluorine side or away from the cloud. It's not always away from the cloud, just this time it's away from the cloud because we know the fluorines are pulling the bonded pairs away from the phosphorus. And we put a little plus sign on the positive side. Let's do number 4. I, Cl, 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 Cl. Well, chlorine has 7 valence, and iodine has 7 valence. So let's do 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7, 4, 6, 7. And iodine brings in 7. So we use 1 here, 2, 3, 4. And remember, here's the trick, I get an extra 1 here. Because it's minus, and minus means an extra electron. So let's treat iodine as if it has 8. And I just used 1, 2, 3, 4 from the iodine. That leaves 4 more. So there must be 2 unshared pairs on iodine. So what do I have? 4 bonded atoms and 2 unshared clouds. 4 and 2. 4 bonded atoms and 2 unshared clouds. Square planar. Also remember it was -1. Is it polar? Well, what's the electronegativity difference between Cl and I? It is 3.0 and 2.5. So I'm thinking my previous answer was wrong. The difference is 5. So let's do, it is polar toward the chlorines. Oh, excuse me, I was right. Watch this. Square planar. No matter how you cut it, you can't find the positive and yet the negative side, because this is the chlorine, negative, 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 negative. And these are going to shrink in. So you get sort of a positive, but they cancel it out. In every equal direction, it's negatives, and equal directions, positives. And so you can't draw a line through the middle and find the negative side and the positive side, or the negative side and the positive side. This is nonpolar. Polarity 2, let's try number 5. Cl with 3 Fs. So Cl's in the center, F's around in some fashion. It's not too important exactly where you place them. On your periodic table, you find out that Cl and F are in the column that have 7 valence electrons. So let's use those and make some shared pairs. So I have 2, 4, 6, and a 7th one on fluorine, and we'll repeat that all 3 times. And chlorine has 7, right? So I'm going to use 1 to make a shared pair here, 2 from chlorine, 3 from chlorine to make a shared pair. I used 3 out of 7 there for chlorine. That means I have 4 left over. So I have 4, that's 2. I have 4 left over. So what shape do I have? I have 2 bonded, 3 bonded atoms and 2 unshared pairs, 2 clouds. It's this, isn't it? T-shaped. So this is T-shaped. Are these polar bonds? Well, the difference between them would be the difference between 4 and 3. So yes, they are polar bonds. And remember, in this case, these are the F atoms. That's the Cl. The F is a 4. The Cl is a 3. So is that a polar bond? Yes. The bonded electrons in the middle are getting pulled toward the fluorines. And so, this one's coming out of the paper, by the way, at 90 degrees to this line here. But we're looking at it from the top a little bit. And so what I could say is I could draw a line through the middle so that the back side was very different from the front side. The back side has only clouds, and the front side has this atom sticking out here. So in general, the polarity has moved toward the fluorines. That's some up, that's some down, and that's some out, but it's very much not back in. So what I'm going to do is I'm going to say that the polarity is away from the clouds side. I know that mine doesn't exactly look like theirs, but I just demonstrated to myself that the polarity is away from the clouds, so it's away from the clouds. And on the plus side, we put a little line there to make a little plus sign. Double check. Is this a plus or a minus charge? Does it need a brackets with a charge? No, it doesn't. Did I make a distributed shared double bond, a resonance structure? No, I didn't. But I did make one little weird thing, which is the chlorine now is not a standard octet. It doesn't have 8 shared electrons. It has 2, 4, 6, 8, 10, which is an octet violation. Let's do number 7, CO2. COO. So, carbon has 4 valence, oxygen has 6, so I get 6 and 6 is 12, plus 4 is 16 valence electrons. It's usually easier with these oxygens if you just put 6 on there and see what you can get. There's my 6 and my 6 from my oxygens, and now I said I have 4 more from carbon. Well, I'm going to have to use those electrons here as my bonding electrons, because every bond is a shared pair. So there's 2 of them, there's 4 of them, and I'm out of valence electrons, and I've used them all up. However, carbon is very unhappy with this situation because it Venn diagrams as a 4. And what I mean by that is we could do this, and the oxygen feels like it has 8 outer electrons, and it's happy with that. And the same thing happens over here. But the carbon, even though it crosses over here, that's what I mean by Venn diagram, it feels like it has 4 valence electrons. That's not going to live with that. It's going to get grabby. It's going to start grabbing pairs. And what we're going to get is it's going to grab one of these pairs over here. It doesn't matter which one you grab because they're not really sitting there still anyway. This is just our fakey diagram, so we get the general idea. They're not just sitting there. They're whirring around at light speed. So we'll just pick one. It doesn't matter because they weren't in any certain position anyway. And there I grabbed one. And there I grabbed another from the left side. And now everybody feels like they have 8 valence electrons. This is not a resonance structure because I don't have to take my double bond and spread it around. Everybody has a normal double bond. What do I have? A center atom with 2 bonded atoms and no unshared pairs, and that is this, linear. Is it polar? Well, we could go to the electronegativity chart, except it won't really matter because the difference between this on the left will be the difference between that on the right, and they're in completely opposite directions. It doesn't even matter what the difference is because there's no way to draw a line through the center point. Keep trying to draw one, but you can't find a way you can get a plus side and a minus side to this molecule. You always get the same thing. In fact, we could go and actually do it even more thoroughly. We could go into the electronegativity chart and we could say carbon is 2.5 and oxygen is 3.5, so the difference is 1, and these are polar bonds. And so this end is a little bit negative. It's changed. That's our symbol for a little bit of change, negative. And this has changed a little bit, negative. And so the carbon is a little bit positive. You don't actually have to write all this in. I'm just trying to be helpful. But the point is that it's equally as negative on both ends, and you can't find the plus side. There's no way to rotate this or mentally cut this through the middle where we get both a plus end and a minus end. We can't find the plus end, and so this is not polar. How about we do our classic water? That is number 11. Okay, so how many electrons do we get? We get valence 6, valence 1, valence 1. So that's 8. So I got to use 2 of them here and 2 of them here. That leaves me 4, and they sure don't go in the hydrogen. Hydrogen can only manage 2, so they go in the oxygen. An unshared pair and an unshared pair. And what I have is this kind of bent molecule. So what's the difference between them in electronegativity? And does it even matter? Yes, it does matter, because I can very easily put a line right across here and say there's the H side and the clouds side. So maybe I can find a plus side and a minus side. So what are the differences between H and O? O is 3.5. H is 2.1. So the difference is 1.4. That's very polar. It's polar toward the oxygen. These bonds here are getting pulled toward the oxygen. And what that'll do is it'll make the oxygen a little bit negative because it has these electrons more of the time. And these clouds will even bulge out. You don't have to draw this, I'm just going to do it anyway. They'll even bulge out even bigger. So is it polar? Well, are the bonds polar? Yes, they are, because the difference was above 0.4. It was 1.4, wasn't it? Which direction was it? Toward the oxygen, which actually then goes even more toward the top, if you want to call it the top. Are the sides identical? No, they're not. Is it polar overall? Yes. It's polar toward the cloud side. And this side becomes the partially positive side. The hydrogens are not able to hold on to the electrons very much. And if you're becoming less negative, you're becoming more positive. What shape was that? Bent. Did we use any double bonds? No, we don't have to count that. Is it an octet violation? No, because the oxygen thinks it has 2, 4, 6, 8 valence electrons, which is pretty normal. Is it plus or minus? Do we need brackets and a charge? No, we don't. And we're done.